Hi students, welcome to Madras Math Kernel. Today you are going to see about the concept and the theory part and also the example explanation required to work out the exercise 1.2. So first one is your theorem 1.2. So what your theorem 1.2 says? It says it is the other name for theorem 1.2 is fundamental theorem of arithmetic. So what it says, every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. So what do you infer from this statement? For example, you take 2, 3, 5, they are nothing but the prime numbers, and you also consider the composite numbers 4, 6, 8, they are the composite numbers. So as per the theorem, what it says, you can write every composite number as a product of the other prime numbers. That is, for example, if you take 6 you can write as the product of 2 into 3. You may write the factors of 6 as 2 by 3, and your friend may write the factors of 6 as 3 by 2. So the order, they can be different. One friend will be writing like this. If you have some more factors, the other friend will be putting the other factors as first. So the orders of writing the prime numbers, it may differ, but the factorization is unique. That is, the factors appearing for a particular number, it is going to be unique, right? So this is what this theorem says. A composite number can be written as a product of the prime numbers, and everyone whoever is finding out the factorization of the particular composite number, the factorization is going to be same. Whoever performs a factorization for that particular composite number, the factorization is going to be same, but the order of writing the prime factors, they may vary. This is what your theorem 1.2 says. And then next, coming to the example 5. So what is your example 5? Consider the numbers 4 to the power n, where n is a natural number. Check whether there is any value of n for which 4 to the power n ends with digit 0. So you are given with a number, you are going to consider the numbers which comes by substituting n is equal to 1, 2, 3 here. For example, the powers of 4, you are going to consider the numbers you are getting by expanding the powers of 4. For example, here 4 to the power n means you can write it as 4 to the power 1, 4 to the power 2, etc. up to 4 to the power n, you can write down. So where n is a natural number, so n takes the value from 1 to n. Check whether there is any value of n for which 4 to the power n ends with the digit 0. So you have to check whether there is a value for n, so that on expansion of this 4 to the power that particular n should ends with the digit 0. That is, the number on expanding 4 to the power n should end with the digit 0, right? That is, for example, if you are taking 4 to the power 5, on expansion of 4 to the power 5, you should get a number which ends with 0. So that n you have to find out, right? So coming to the solution part, for any number to end with digit 0, that is, whatever be the number, if it needs to end with 0, then it is very clear that it should be divisible by 5. It is also divisible by 10, but the prime factor there is 5. It should be divisible by 5. You have to see the prime factor. So for all the numbers ending with 0 digit, compulsorily they should get divisible by 5. Therefore, the prime factorization of 4 to the power n, they should also contain the factor 5, right? So this is what the information we are getting from this statement. But rewriting the given 4 to the power n, so we can write 4 as 2 square, right? So on rewriting this given natural number or given number, 4 is equal to 2 square the whole to the power n. So that is equal to, you can multiply these two powers, 2 to the power 2n. So you are getting 2 to the power 2n. Whatever may be the factorization, whatever may be the number on factorization, it is going to give you only 2 as the prime factor for this particular 4 to the power n. Why? Because everything is going to come as the powers of 2. So even on n factorization or if you divide the particular number by n factors, you will be getting only 2 as the prime base factor, right? So since there is no phi, sure, on expansion, this expansion of 4 to the power n, this won't yield you any number ending with digit 0. Therefore, you can conclude there is no natural number for which your 4 to the power n ends with digit 0, right? Is it clear? Coming to example 6, find the LCM and HCF of 6 and 20 by the prime factorization method. Okay, so LCM and HCF, sure you would have studied in your lower classes. So you have to find out the LCM and HCF of these two numbers. First, I am finding out the prime factorization for 6. It is very simple, it is 2 into 6. And then you consider 20. 20, I know 4 and 5 are the factors for 20. Again, you can split up 4 into 2 into 2. So 2 into 2 into 5 will get you 20. Now what do? You write these prime factors in terms of by adding the powers, right? So here that power of 2 is 2 to the power 1 and power of 3 is 3 to the power 1. Here you have 2 2's, so 2 square and 1 5, so 5 to the power 1. Coming to the LCM you would have studied in your lower classes. So what you will do, first you have to write down the common number, then you have to common prime factor, then you have to write down the left out prime factors. For example, here if you consider these two numbers, 2 to the power 1, 2 to the power 2. So 2 to the power 1 is common for both the numbers. So I am writing 2 to the power 1 first. Then if you see here, I have written this 2 to the power 1 here. The left out number is 3 to the power 1. I am writing 3 here. Then coming to the second number, here it is 2 square. Already I have written 1 2 there. So 1 2 is left out. So you write it here. And then 5 I have not written anywhere. So you write 5 here. So if you multiply everything, you will get 60. So the other definition for your LCM is, it is nothing but the product of greatest power of each prime factor involved in the numbers. That is nothing but, you see what are the the greatest power of the prime factors. For example, if you consider 2 to the power 1 and 2 square here, you can see 2 square is the greatest power. Yes, 2 square is a prime factor with greatest power, right? So you write 2 square here, you can write 2 square, and then the greatest power of 3 is 3 to the power 1 only, and 5 is 5 to the power 1 only. So again, if you multiply all these things, you will get 60. So LCM is nothing but the product of the greatest power of each prime factor. Okay, coming to HCF. So HCF is equal to, so HCF is nothing but highest common factor, just to see the common numbers from the prime factorization. Prime factors. So 2 to the power 1, 2 to the power 2. So here 2 to the power 1 is common in both the numbers. So I am writing 2 to the power 1. Other than 2, there is no common numbers. Therefore, this is the HCF for the given numbers. Similarly, if you see HCF, this is nothing but product of the smallest power. LCM is the greatest power. HCF is the smallest power of each common factor. That is, it should be common for both the numbers, and the power also should be very less, or the small, or it should be small, right? LCM is nothing but product of greatest power of each and every prime factor. HCF is product of the smallest power of only the common factors, each common factors, right? And then you can make a note from the above example that product of HCF and LCM of any two numbers should be equal to the product of the particular given numbers. For example, you consider A and B are the two numbers, HCF of A and B and LCM of A and B on multiplication should be equal to the product of A and B, right. I have explained here. 6 and 20 is the previous example problem what we have seen a little before. So, HCF of 6 comma 20 and LCM of 6 comma 20 on multiplication should be equal to the product of those two numbers 6 and 20. So, if you see here 2 is HCF, 60 is the LCM. So, on multiplication it is giving me 120 and 120, right. It is just an explanation for a clear understanding of this formula. Coming to example 7. So, find the HCF of 96 and 404 by prime factorization method. Hence, find their LCM. So, you should not find LCM in a regular way. You have to find out HCF by prime factorization method. Then what you have to do? You have to find LCM by using the above formula. So, first you do prime factorization for 96 and 404. 96, I have done the prime factorization in a simple way. That is 96. The better, the well known factor for which I know for 96 is 4. So, 4 I put here. So, 4 2s are 8, 4 4s are 16. Again for 24, either 4 or 6 you can write it here. Again for 6 it is 2 and 3. What I have done here is I have written 4 4 2 3 here. Then I have expanded 4 again. Similarly, this 4 also. So, 4 is 2 square, this 4 is 2 square and 1 more 2, 1 more 3. Now, finally, I add up all the powers of 2 and I have written as 2 to the power 5 and 3 are the factors of 96. Similarly, if you see 404 on prime factorization, it is giving me 2 square and 101. So, what is the HCF? Obviously, HCF is nothing but the smallest power of the common factor. Here common factor is only 2, 3 is not a common factor, 101 is not a common factor. So, 2 square is the HCF for the given numbers. Then as per the formula, HCF of 2 numbers into LCM of 2 numbers should be equal to the product of 2 numbers. So, here LCM, if I want to find out the LCM. So, I am retaining my LCM here. LCM of 96 comma 404 is equal to the product of A and B. Here A here is 96, B here is 404 divided by HCF of 96 comma 404. So, on substitution I am getting this term, the final value is 9696. This is the LCM of the given two numbers. And then coming to example 8. Find the HCF and LCM of 6, 72, 120 using prime factorization method, regular procedure, regular method. So, 6 it will give you 2 and 3 are the factors. For 72, 2 to the power 3, 3 square. For 120, 2 cube, 3 and 5. So, HCF is nothing but the smallest powers of the common factor. Here 2 and 3 are common. If you see these numbers you will understand. So, 2 to the power 1, 2 to the power 3, 2 to the power 3. So, 2 to the power 1 only you should take because that is the smallest power. And here if you see 3 to the power 1 is the smallest common factor, smallest common number, smallest common prime factor. And going to the, so 2 into 3 will give you 6. And coming to the LCM part, so LCM is equal to what? First you have to write the highest power of each and every prime factor you have to write. If you see here 2 cube is the highest, so I have written 2 cube. If you see here 3 square is the highest and then 5. So, if you multiply everything you will get 360 as the LCM and HCF is 6. So, that is all the concept and example problem explanation pertaining to exercise 1.2. Thank you students.